But because we are following the loop 1 or the mesh 1, we are looking at going in this direction. The net current is therefore I1 minus I2. This is the current that will come here to multiply that impedance. I1 minus I2 bracket. So now I can rub this. I hope things are recording at the background, so please don't play around. I don't see the recording now. And then when we come to the 5 ohm, again you will see the same scenario, that the current I1 is being opposed by I3 because I3 is opposite to I1. So we are going to write plus 5, which is the impedance, times I1 minus I3. Right? So now we just have to simplify this equation. Is that a question? No. Okay, thank you. So we have to collect like terms first. There is I1 here, which is multiplying by 10. And then there is also I1 involved here in the minus J4. There is also I1 involved in 5. You can ask.
So I want to ask that, oh, diagram, set diagram only.
There.
Yes. Okay, we need to find out IO.
That's correct.
Okay. I1 is equal to IO.
That is correct. You can see that from the diagram because IO is the current flowing in the 10 ohm resistor. We are using the loop.
There is never a junction behind IO.
Sorry?
There is a junction behind IO.
What do you mean a junction behind IO?
I mean there is a splitting of current.
We are using the current mesh method. We are not using the branch method.
Current mesh method.
We are using the mesh method, where you have to define the loop or the mesh currents.
Yes,
that's why
loops.
Yes. So where is the node coming in? Because we never spoke about this node. We're talking about the meshes.
I think they are analysis.
Yes, sir. I understand.
Okay. Right.
Yeah.
So we now simplify this and we just collect like terms, right?
I'm just split it in screen up, right?
You see, if you want to talk, you are not disallowed to talk, but do it in an orderly way. Say I have a question, you see. You don't just talk in the middle of somebody talking. That is rude. So we collect all the terms in I1. Let me increase the thickness. So I1 here is multiplied by 10. And if you look there, I1 is multiplied by 5. And both 10 and 5 are real. So this we can cancel. This we can cancel and write together as 50. Then here, I1 is multiplied by the complex, which is minus J4. So we can bring minus J4 in here in brackets because there is no more I1, and outside we write I1. Then there is I2. There is no other I2 term apart from this one. So that negative and this negative, it means plus J4 I2. And then lastly, I3, which is simply multiplied by 5. So it's minus 5 I3 equals to 50. So that is your mesh equation for the first loop. This. So you keep that one. Now notice that there are 3 mesh currents. It means you're going to need 3 equations. All right? You're going to need 3 equations to find this solution. Now let's go to mesh 2, which is this one. Now the difficulty we have with mesh 2 is apparent because of this current source, which is splitting these 2 meshes. Remember, the mesh current works on Kirchhoff's voltage drop law, KVL. Now, this is a current source. We will not be able to write a KVL equation here. There is no impedance that you are going to say Ohm's law is for current times this impedance. You cannot. Right? But what you observe, if you take this source here, if I just repeat it right here so that it's clear. Let me make the pen thicker. All right, there you go. If I take the source, it's a current source, which is 2 amps. The angle is 0, so I'll just write it as 2 amps, right? And that arrow shows the direction which the source is supplying the current. Now, if you look, the mesh current I2 is flowing in this direction. This is I2. And then the mesh current I3 is flowing in this direction, which is opposite to I2. So it's flowing there. So this is I2. I3, sorry. But this current here from the source is 2 amps. That means I3, because I3 is the current flowing in the same direction as the source as it's given, minus I2 should give us nothing else but 2 amps. Right? So I3 minus I2 gives us that current. That is your second equation. So we can write it here. 3 minus I2 is equals to 2. So this here I can take out. It was just to explain. Right? So I'm going to box this one again. Now we have 2 equations, 1 and 2. We are still short of 1 because there are 3 unknowns. We have to find the other equation. How do we get the third equation? To get equation 3, when you have got this scenario here, you create what we call a super mesh. What do we mean? I'm going to illustrate it here. I'm going to draw my diamond. All right. Then I'm going to show the impedances. This is my capacitor, which is minus J4. This is my inductor, which is J8. Then this is another capacitor, which is minus J8, J6, sorry. And then lastly, my resistor, which is 5 ohms. 5 ohms, right? Now you'll notice that I did not draw the middle branch with the current source. I've left it out here. The reason why I've done that is because I'm going to create a super mesh. And the super mesh is going to be this loop. All right? That is what I'm going to say is a super mesh. I've removed the current source. Remember, I've created a loop which has got 2 other loops. All right, this is now a loop with 2 meshes inside it. And I'm just calling it super mesh, right? So I'll repeat it here. Right. But for this mesh, I am not going to define new currents, right? I'm not going to define a new current. Why? Is because I do recognize that if I'm going to apply KVL around this, sorry, a question? Okay. If I'm going to create, to write a KVL equation, this impedance I have, and I have all these 4 impedances in the 4 arms. The currents, I already have them. If I'm going to go through this direction here, remember that direction is this. If I'm going to write the first equation for this minus 4, you must realize that the current I2 that we defined now, I2, I'm just going to draw that one, right, is in this direction. This is I2, right? I2 here, I2, right? It's in that direction. And then remember also there is I1 in that direction. We already defined these 2 currents. So, but we are looking at this direction of the super mesh. So the net current for this here, it cannot be anything else but I2 minus I1. So I'm now writing a KVL for the super mesh, starting with this impedance. So I know it's minus 4 J in brackets right, minus 4J in brackets. The current is I2 minus I1. So I've written a KVL, voltage drop, for this one. When I come to J8, this arm here, you'll see that there is no other current here but I2, which is flowing in that same direction as this current here in the super mesh. So the voltage drop for J8 cannot be anything else but plus J8 times I2, this current, all right, this mesh current. And similarly, when I come to J minus 6, there is no other current flowing here. It is simply I3. And I3 is in the same direction as the super mesh. So I'll simply have minus. Then lastly, I'll come to the 5 ohm. Now you'll see that in the 5 ohm, I3 is flowing in the same direction as the mesh, super mesh.
Sorry, sir.
I1 is, I'll come back to you, just hold on. So this is I3 minus I1 times 5. That's the voltage drop. So it's plus 5 brackets I3 minus. There is no voltage source. We have written all the voltage drops, so that cannot be equals to anything else but 0. There is no source. Okay, my friend, you can ask.
Let's say I3 is in opposite with the super mesh. Beso bhala kanjani?
I'm not too sure I understand you. If you are asking, you see, if you draw this resistor here, I'm going to draw it separately here. It's like this, right? Just that arm. If you look at the mesh currents that are flowing, this is I1 here. It's in that direction. So there is I1, which is here. If you look on the other side, there is also a mesh current I3, but in the opposite to I1. So this one is like this. This is I3, this. So this is I3. But the mesh current that we are looking for is in that direction, right? So it's in the same direction as that. So if you had defined this as current I, we don't define, because we don't want to increase the number of ones. But if you call it whatever you want to call it, I is actually equals to I3 minus I1. If I want it to be I3 plus I1, you see, they will be adding. Does that help?
Yes, now I understand. Thank you.
So now, if you see, we only have to simplify the as we before, right? So that's what we'll try and do now. This minus J4, write it neatly. So let's try and simplify this, all right? We start off with I1. There's an I1 here. This is minus, so it's going to be plus, but it's complex, all right? So this one we know. There is no other I1 but this one. And this one is multiplying by minus 1. So over here, we can write minus 5, because it will be 5 times that one. Then this one will be plus, because it will be minus times minus J4 in brackets I1. Then we go for I2. There's an I2 here, which is complex, minus J4, which complex, plus J8. So this and that is going to give us plus J4 I2. This is positive, that is negative. So those two are taken care of. And then lastly, we are going to have 5 in brackets for this guy here. And then this one is complex, it's minus J6. That one is taken care of, multiplied by I3, all equals to 0. Right? So now we've got our 3 equations. With 3 unknowns, we are able now to solve this system of 3 simultaneous equations to find the 3 currents. So let's just group these equations together in this, right? We are going to start with 15 minus J4. I'll just write it here. 15 minus J4 brackets I1 and then plus J4 I2 minus 5 I3 minus 5 I3 equals to 0. Then we collect the last one, which is here, I2 minus I3 minus I2. In other words, this one is minus I2 plus I3
Question, sir.
equals to 0. Okay, let me write, finish. Just hold on to your question. So this is minus I2 plus I3 equals to 2. If you want, you can write 0 I1. Right? So those are our 3 equations just gathered in one place. Yes. Go ahead.
Okay, I see.
Okay,
I
sorted.
missed that equation 1 is fine. It's fine now, so I can follow.
Okay. So now we have gathered all our equations in one place.
Excuse me, sir.
Can do now is solve this simultaneously. Hello? Okay, no one responding. So we can gather this and write for inverse times B. Now remember A. So here I'm going to write it here in matrix form, right? This means you are multiplying. There is a multiplication there, right? So this is I1, I2, I3 equals to right? We are going to follow the same order here. Something is not right here, right? But this one, I don't think it is. This is the last equation. It's 2. So we are taking them in that order. So we can write here 0, 50, and 2. Right? Those are right-hand side values. And then the last one The coefficient for I1 is 0, so we can write 0. The coefficient for I2 is -1, -1. And lastly, the coefficient for I3 is 1. So we are done with this equation. Then we can go to this one. The coefficient of I1 is 15 minus J4 minus J4. Then the coefficient for I2 is J4. Then the coefficient for I3 is 5 minus J6. So like that. N plus J4. Then this is 5 minus J6. Is that? You have to check this equation. Something is looking a bit suspicious here. Well, I hope we have written these equations correctly. But anyway, that's what we are finding, right? This is the last pillar, this equation here. Right? If anything is amiss, you can check in the notes. It's again solved, right? But for what we got, this is the I'll take out this one. This is A multiplying that. So what we need now is to find the inverse of A.
Sorry, sir.
Once we have the inverse of A, if we multiply it into carry on. Go ahead and ask.
Sir, I was removed from the meeting, so I'm a little bit lost. How did you get after finding the equation of current? How did you get the matrix thingy? Ax is equal to B.
Okay, Sisi, what is the size of this matrix?
Sorry, sir.
Where my case, what is the size of this matrix where I'm hovering at? Hello?
I don't.
I'm saying, can you give me the size of A, this matrix which I'm hovering on? What is the size of that matrix? I'm not too sure if the student who asked the question is still connected. Are you still connected? Okay, of those who are connected, anyone have the same problem?
No, sir, but I have a question about this matrix.
Yes,
Hello, sir?
I'm listening.
Okay, sir, there by the first column where you got -5 plus J4, and then you have J4, and then you have 5 minus J6. Isn't it supposed to be 5 there by the top, not 5 minus J6?
Yeah, you mean here? Do you see my cursor?
Yes, sir.
Are you talking about here where I've circled?
No, the last one.
This one?
Yes, sir.
Okay, remember this is the last
Yes.
equation, you see, which should be this one. Correct.
Oh, okay, sir.
This is the last equation, this one. So the term that
Oh,
multiplies I3 is 5 minus J6, which is this.
oh, okay, sir. I can see it. Thank you.
The only thing I said, we need to go back, and that is your homework. Just make sure that, you see, these equations here are correct. You just need to make sure that simplifying them to this, where we are removing the brackets and collecting the like terms, are correct. But according to the working that we have done now, this is what we are getting. The first term is 15 minus J4, which is this 15 minus J4. That's the first equation obtained plus J4, which is this one. And the last term okay, let me start again, right? You see, this is the last equation. The coefficient for I1 is 0 because there is no I1, which is that 0. The coefficient for I2 is minus 1, which is this. The coefficient for I3 is 1, which is that. So it's that equation, right? So this equation, we're done with it. The second equation, which is a 50, there is your 50. This side. Now, I1 is multiplied by 15 minus J4, which is that. I2 is multiplied by J4, which is this. Then I3 is multiplied by minus 5. Look what we wrote is not correct. Right? That one should be minus 5. Like that. Yeah. Then the last one is minus 5 plus J4, which is this. Then the next term is plus J4, which is that. And lastly, 5 minus J6, which is this. So that looks more like it now, right? So the next question is to find the inverse. I told you that if it's a 2 by 2 matrix, I've already shown you how to find the inverse. If this here is what you are given, right? I'm just giving an example. If this is a 2 by 2 square matrix, if you want to find the inverse of this, it's simple. The determinant 2 by 1, which is 2, minus this times that, which is 21. So your answer there is minus 19, right? Then it's minus 1 over 1 over the determinant, right? Then you change the positions of these two here, meaning the 2 goes there, the 1 comes here. Then the 7 and 3 change sign, so they don't change positions, signs. So this becomes negative, that becomes negative. That is the inverse for this matrix here, finish. But when this is 3 by 3, it is not easy to compute the inverse. I hope you have done that in maths, right? When you're using Cramer's rule and things like that. But for the purpose of this course, my interest is not for you to be able to show me that you can calculate the inverse. That's not my purpose. My purpose is for you to be able to write these equations, the mesh equations. Even if you had 5 unknowns, that means you had 5 meshes. you'll still be able to write those equations and put them in this form. Once they are in that form, you can use a number of tools to solve these equations. I'm going to show you one tool. Those of you who are, well, you can try it even on your cell phone, you know, because you are online. Just wherever you are, just go to the internet. That's what I'm doing now. So you do it on your side. Just go to the internet. Let's see if we can get something here. Then say online. Online linear. All right, say online complex linear equation solver. So you'll say online complex linear equation solver, then off you go. You are going to get a number of possible tools. I'm looking for one that would be not this one. Let's look for another one. Look for one which says simultaneous equation solver. Okay. I've got one here which I've used before. You look for simultaneous equation solver. Now, because I want to share with you the screen. All right. Now, there are many of these tools, right? This is just one of them. Now, please remember, I'm not saying you mustn't know how to do this manually. You should be able to solve it manually. But the nature of complex analysis is time consuming. If it's a 2x2, then you still can use this tool, but you will be expected to know how to solve it manually. But if it's 3x3, in other words, you have got maybe 3 node voltages or 3 mesh currents or even more. If it's a network, if you are going to solve, say, network from LASI, you can easily have nodes that run into the thousands and mesh currents that run into the hundreds. So you see a set of simultaneous equations with 100 unknowns. You won't be able to do that. So you have no other choice but to use computers. That is why I'm showing these tools. So here is a tool. I hope we can all see it. This tool is used to solve the complex equation. Our equation has got 3 unknowns. You see, by clicking here, I've reduced the squares. If I have more unknowns, 6, I would make it large. I would even go to 8 to 7 unknowns. You see, it's increasing. But I only have 3 unknowns, so I will reduce it accordingly. And in these cells here, that's where you put the coefficients that we have defined. Notice the way it's written, right? There are examples that are given. So I'm going to enter starting from the first row, which we said was -5 plus J4. Notice that it's not written J4 in here. It's written 4J. So I'll write 4I. Then the next coefficient is J4, which is 4I. And then the last coefficient is 5 minus J6, which is 6I. And then, of course, here it stays 0. The second row, it's 15 minus J4, which is 4I. And then the next one is J4, which is 4I. And then this one is -5. And then lastly, this is 0, remember. And that one is -1. And this one is +1. So I now have to put the constant terms here. I've got 50. And there, I've got 2. And this one falls out, right? It's only 3. Like that. So I have put my coefficients according to the matrix. This is the matrix A. This is the matrix B. Now, if I execute, it will come back with an answer. So the answer is what we see here, all right? I'm going to write it over here and then unshare this. The XX1 is the value of I1. It's given in rectangular coordinates, so it's 5.0. I'll call it 5 plus J. You can use J and I interchangeably, it's the same. 53 amps. And then I2 is given as 3.37 plus J 0.24. And lastly, I3 is given as 5.37 plus J 0.24. All right. So those are the values of the unknown currents. You were asked to find I0. So your I0 is that one, I1. You see? So if your equations are correct and all the coefficients is given are correct, then this will be your correct answer. You have just used this tool to help you to solve the complex equation. If you want it in polar form, then of course you can convert here in polar form, or you can find other solvers that will do that for you in one shot. So this is what I wanted to teach, and it's almost time, just a few minutes left. I don't know if there are any questions. I will not be able to do all the examples, definitely. but there is no new information. You just have to apply the same techniques that we have tried to illustrate and work the two examples on each of those techniques. These are the main techniques that we use. Now, you may not see the value of why we changed to this form, the matrix, but I've already told you that if you are going to solve a network corresponding to the electrical distribution system formulas, you see the nodes and the branches run into thousands. That means 1,000 unknown currents or voltages, not voltages, I1, I2, I3, all the way up to I1000. Can you solve such a network using manual means? No, you cannot. It's too much. But to be able to use a computer, you should be able to assemble that network into this matrix form. Once you have this matrix form, it is then easy to do the number crunching in a computer application that will solve and give you, be it voltages and currents. That is where the real use of the matrix form lies. And after you do a number of examples, you'll see that at a certain point, you will be able to write these matrices even without writing the equations. You look at the network and you will be able to write this A matrix, you will be able to write the B matrix, and therefore right away feed them into a computer package to calculate whether they are voltages or currents. And once those are determined, every other question you may ask or to find out about current flows, power, you will be able to calculate it. And therefore, you will say you have analyzed your circuit. All right, are there any questions? Any questions? Now, before I leave this topic, please notice that all the rest of the
Yes, sir.
examples that PowerPoint are there for you.
Sir. Sir, can you please repeat for us the solution?
What do you want to repeat?
The solution.
What do you mean repeat it? Do you want me to read it out?
Yes, start from X1, X2, and X3.
Why you can't see it?
Yes.
Why?
No, I need to tell me how we get this.
No, but you know, the starting point is this. You see here, where you write the matrices. You see, that is the starting point. Once you have the matrices, I did not work out the solution. I showed you this online tool, which I'm sharing now, which is, you can see right here. Do you see my screen?
Yes, I see.
Do you see where the cursor is?
Yes.
Yeah, that is a general solution. It's telling you that it can solve equations of this. So once you write your equations like we have done, you see in the screen that I was sharing on one page, one note. Once I've got those numbers, I'm now putting those coefficients right here because this is the tool now. You see, these are the coefficients from the first equation, coefficients of the second equation, number 2, and lastly, number 3, coefficients from the last equation. Once I fed those numbers into these two here, I'll just say execute, and then it will calculate and give me the answers. So your X is here, is your unknowns. We are not dealing with X. We are dealing with current, you see. But this is just a general tool, so you should know that X1 is your I1, X2 is your I2, X3 is your I3. That's all. Okay.
Yeah, okay, sharp.
There are many tools you need to exploring. So now you don't have an excuse to do all the rest of the. You must be able to do 2 things manually. Only when it's higher dimension, 3 by 3 or 4 by 4, then you can use this. It is okay because you understand how to solve manually. It's just that it's too much work to solve 4 simultaneous equations, especially when they are involving complex numbers. You spend your whole afternoon trying to figure out, the correct answer. So why bother if you can get help here? So my last comment on this section here is to refer you to the rest of the examples. You see how I know certain things are not within control. You'll see that you don't interfere with your colleagues' time. And I believe they'll appreciate that. You can't control your background, that's for sure, but you certainly can mute. Right, so this is where I took the example. You see it's solved, the I0, it's 5.07. And if you change this to polar form, I'm sure this is what you are going to get, 5.07, whatever the angle is. So there you have it. Now, these rest of the examples in the slides, you need to go back and do them. There are quite a number of examples which I did not do, but they are fully worked out here. So what you are invited to do is to follow the steps, write the equations, and yeah. The last thing I want to mention to you is just 2 concepts, and then, we'll jump to something else. So let me add here maximum power transfer. Let me say superposition and maximum power transfer. All right, I will go back and unshare. I will share my OneNote again. Yeah, there are 2 things that I would like to talk to you about in closing this section on network analysis. The type of circuits that we have dealt with, or that we deal with in this course, for that matter, are called linear circuits. There is no nonlinear elements in these circuits. What do I mean by that? I will not go into details, but let's look at this simple example. You've got a source, or an impedance rather, right? And that impedance is fed from two voltage sources. I'm using voltage sources here, but it could well be voltage and current, or current sources, you see. The type of impedances, be they inductors, capacitors, and resistors that we are dealing with here, they've got a linear relationship with voltage and current. Linear in the sense that voltage and this impedance, they are related by this equation. You see, current and voltage are linear if that impedance is constant, which is the case most of the time for a given circuit. Now, there are systems which do not obey this kind of equation. For example, you may have voltage is equals to current squared times impedance. This is not a linear, law, because it's current squared. This is actually a parabolic relationship. If you do that, the voltage will be a parabola. In this case, it is a straight line. It's a linear relationship. So if you have got linear circuits, even if you don't really understand or remember what we mean by linear, just understand that for the type of circuits that we are dealing with in this course, if you have got 3, 2, or more sources connected to an element or elements, the effect of these two sources on the impedance is just as good as taking the effect of one source at a time, then adding the two effects together. What I mean is like this. If I say here, what is the current flowing in IZ? I can take the current flow due to V1. Sorry, this is supposed to be V1. This is Z. Remember, I've now removed this other source. So I remove this and I calculate the current due to V1. Of course, that is all. So I can call it I1 is equals to V1 divided by Z. Then I'll do the same thing, but now disconnect V1. So I'm going to have this situation, V2 connected to the impedance like that. And the current here is going to be Ohm's law, V2 divided by Z. So now the law of superposition states that the net effect of having V1 and V2 connected together simultaneously is such that the current in Z is going to be this I1, V1 over Z, plus V2 over Z. In other words, we have combined those two currents. That is what we call superposition. The net effect of the flow in a particular element, in a particular branch, when there is the number of source time, calculate whatever variable that you are worried with due to that one source, disconnect that source, add another one, calculate, and then at the end, add the net results of those calculations you are going to get the result of having all those sources connected at one time. That is what we call superposition principle, right? Now, so we go to maximum power transfer. When you have a source, remember a source has internal impedance of itself. Right? If you connect this source, the source is supposed to supply a load with power. So on the other hand, if I've got a load, this is Z load now connected. So I'm supplying power to this power. The maximum power states that maximum power from the source to the load is transferred if ZL is equals to Z in complex conjugate. That bar on top means complex conjugate, right? For example, if the internal impedance is 3 plus J5, then for maximum transfer of power from the source to the load to happen, you should have a Z load of 3 minus J5. That is what this load should be. If it's not like that, it means you are going to waste some power. So maximum transfer power, power transfer from the source to the load, when the impedances are complexes, happens when the load's impedance is a complex conjugate of the source impedance. That is when you get maximum power transfer. And of course, if you have done this when you're looking at resistors only without considering reactive components, you would have been told that maximum power happens when the load impedance is equal to the internal impedance of the source. Of course, you can see here now that if this is 3 plus J5, and we are saying it happens when this is a complex conjugate, then if we add these two, we are simply going to get 3, right? In other words, this is 3. Effectively, the impedance, the reactive components cancel out each other, and you have 3, 3, which falls back to the same result. So those are two things which you find in the notes. They are not on the slide, but they are in the summarized notes. There is a 63-page document that is on Teams, I think, and also on Blackboard. You can go read what when it talks about superposition principle and also maximum power transfer theory. With that, ladies and gentlemen, I want to close this chapter, and you can ask closing questions before I move to what I wanted to talk about. I won't have time to look at the test. Just a few comments on the new topic that's coming, and then, we can close for today. So I'm opening the floor for questions. If there is any students here who were hoping to write test 2 makeup, I was a bit uncomfortable to do it because I did not know the picture, the outlook for load shedding. I did not want to set a test where I could give it open for a long period. I'm trying to, to be fair to all students, so that we all have the same chance, not get other people, doing some other things which are funny. So if I cannot get a venue so that you sit down and write under supervision, then it looks like we don't have load shedding. So I would schedule the test to be written simultaneously by all students at the same time online. those who want to write the makeup. That will be before the 20, the date announced for the second test, which will be this week, Saturday. Test number 2. Test number 2 is obviously going to cover network analysis and things that we did concerning power and power factor correction. That is what we are going to cover. So I want you to ask the questions for now.
Yes, sir.
On what? Yes, carry on.
Sir, for the test, sir, when we're getting our marks, let's say you write the second test and you get a mark lower than the first test you wrote. So which mark are you taking?
I take the higher one.
Oh, all right, thank you.
Mm-hmm.
Scope is the same, sir. Scope
is the same.
All right, all right.
Mm-hmm. Any more questions?
I said because people are not asking. Say once again, say for the second test, say the scope is it